This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and today my guest is Dr. Paul Dawkins, who's an assistant professor of mathematics education in the Department of Mathematical Sciences at Northern Illinois University. Paul, thanks so much for being here.
Yeah, glad to join you.
We are going to be talking about Paul's article that's published in the journal For the Learning of Mathematics, and that's entitled When Proofs Reflect More on Assumptions Than Conclusions. But Paul, I'm going to put that article off to the side for a second. I want to back up and ask you about your graduate school experience and your dissertation.
Okay, so I went to graduate school at the University of Texas at Arlington in the middle of the Dallas-Fort Worth region, and I was in the math department, and I came in actually not quite sure if I wanted to do math or math ed, although I was leaning towards math ed due to some good advice I got from my undergrad professor. And so after my first semester, I started reading papers and such with James Epperson, who became then my advisor, and we did some master's level research together, and then I did my dissertation studying teaching and learning of undergraduate real analysis, or what's often called, I guess, advanced calculus. And so I kind of focused a lot, some of the publications that came out of that focused a lot on students defining activity in undergrad real analysis, because the definitions in that course are pretty challenging and are pretty heavy accomplishments for students.
Yeah, I've been pretty fascinated with some of the work on defining, because to me it's such an important mathematical process, and a lot of times it's kind of just taken for granted. There's maybe attention given to proving and reasoning, obviously, and then maybe some attention that goes to conjecturing, but I think we need to, expand it even more to really make defining part of this whole umbrella.
Yeah, and that comes up in the current paper that I think we're discussing today. That it really is kind of an essential piece of what's going on, and there's a lot of literature about how students treat definitions, mathematical definitions, in a way that's certainly not very compatible with mathematical practice, and certainly a lot of my research has been interested in how do we create learning environments in which students become more acculturated to the way that mathematicians treat definitions, the way they work with them, that kind of thing.
Mm-hmm. So were there some specific things that prompted you or motivated you to kind of think about your approach to teaching proof in this way? I should say, in the article and For the Learning of Mathematics, you really deal with the foundations of mathematics and axiomatics and defining and proving all wrapped together and interacting with one another. So with your instructional approach, where did that really come from?
Yeah, there's kind of a couple of antecedents to that. First off, in my dissertation work, I ended up studying a professor who was a mathematician, but had a very non-conventional, non-traditional way of teaching, and there was a lot of really wonderful aspects to the way that she taught that I ended up kind of looking through the literature for tools to really account for what she was doing in the classroom. And some of the most fitting tools I found came from the literature on realistic mathematics education, Freudenthal and Gravemeyer, and there's a group of undergrad math ed researchers who have been adapting those tools for a while now. But this idea of teaching math, first off, by putting students in, getting them engaged in the activities of mathematics, turning kind of nouns of definitions, theorems, and proofs into verbs of defining and conjecturing and proving, and moreover then finding kind of ways for students to really make those activities experientially real, something that they feel like they have some control over and can really engage in. And what I found in my dissertation was engaging in defining helps students reflect on the nature of defining, which is, in the end, kind of not surprising when you state it that way, but is pedagogically really powerful. And so then moving on into future studies, it seemed like kind of a natural extension to move into axiomatizing, looking at how students can be engaged with the process of creating and kind of installing axioms, and how that influences their view of the kind of the formalized mathematical game. And you really mentioned an important point, which is that I see all these things as being intimately intertwined. In fact, in the paper I kind of cite Mariotti, who says, a theorem can't be understood as just a statement of a theorem. It really has to be a triad of the theorem, the proof, and the underlying theory that makes that proof really validate that theorem. And so there's this notion of interconnectedness that is really kind of essentially tied into a lot of what I've been trying to work on here.
Yeah, and you talk in the article too about the fact that these are all intertwined also means pedagogically to kind of avoid the typical approach of giving these definitions. Here are the definitions we're going to work with. Here are the axioms that we're going to assume. And now let's put all of our attention on learning the next theorem, and then the next theorem, and then the next theorem. And in the article, you talk about really complexifying that whole picture. Can you say a little bit more about kind of in what ways you complexified that?
Yeah, so, this is directly coming from Freudenthal, who criticized what he called ready-made mathematics, presenting this to students to where we've already done a lot of the cleaning work. And I'll say it's hard because, when I was working with axiomatizing and as I started to unpack kind of what it would look like to adapt the realistic method tools in axiomatic geometry, specifically neutral axiomatic geometry, meaning that the axioms aren't just about the Euclidean plane. They don't just describe one familiar known object, but it's really we're building a theory that somehow encompasses Euclidean, spherical, and hyperbolic, and many other things at various points. And so there's just this really complicated situation where we're trying to define concepts in a way that not only captures the essential notion, but also somehow affords the way these notions get instantiated in a bunch of different planes. And then axioms, again, we want one axiom that somehow accounts for what happens across examples. And it's really cool for students because, it's an opportunity to do this really direct generalizing and abstracting, taking patterns and trying to articulate them in real clear ways that we can have general statements that apply across kind of quote-unquote examples. Because, really in some ways, like in abstract algebra, this is one of the first times students are seeing this whole complex system as an example, right? That like a geometric plane is an example of this more general thing, kind of like I don't know, like the numbers being viewed as an example of a group or something. And and there's just a lot going on there. And so, one of the tricks in doing this and in this whole project was trying to find ways to kind of devolve those tasks to students in meaningful ways, where I gave them I bounded their choices enough that they could kind of reason about their alternatives and yet still really take ownership of the progress. And I think that's a lot of the issue of realistic math ed in any case. Guided reinvention is how do you both constrain and guide the process while still giving students a lot of latitude and letting them really build on their own ideas and their own activities. And that has definitely been a challenge in the geometric setting. But students do also come with a lot of geometric notions, obviously, spatial ideas. So there is still a lot to build on there.
Mm-hmm, sure. So you have these kind of, grand overarching goals for your pedagogy and things that you want to have your students experience. But then what was the specific mathematical contexts? So you mentioned geometry, but could you just let us know in this article what are the mathematical topics that come up, even though the mathematical topics themselves are not really the point? It's kind of these bigger ideas that are the point. But just to help the listeners, let us know kind of what the topics were and then who these students were that you were working with.
Yeah, so this is a junior level undergraduate course primarily taken by math education majors. So people are training to be teachers. But it's essentially a proof-based course. We have a book that we use. So I adapted all of my activities from a set text that's just been used in this course prior. So in the text, it really starts from an incredibly basic level. The starting axioms are as simple as there are two lines, and every line has 2 points, and how many times can lines intersect each other. And so early on, the theory in this body of text allows finite planes. Almost anything is a plane at this point. It's real simple. We start with 7 axioms, and then those axioms get introduced, more and more axioms get introduced over 9 chapters. There are 21 axioms. And what I like about it is each axiom is pretty bite-sized. Most of them make kind of, small tweaks to the system, so that allows them to all be much more close to maybe some kind of primitive intuition. And so they define early on simple concepts such as a betweenness relation, meaning when is a point between two other points. Hilbert actually just called that an undefined term. He just said, we can say that some points are between other points, but we aren't going to say what it means. This, I think, is derived from maybe an old curriculum developed by University of Chicago years ago, where betweenness is defined in terms of a distance equation. So B is between A and C if the distance from A to B plus the distance from B to C is equal to the distance from A to C. And then also you require that they're collinear. So students are defining really, really primitive basic terms like that. And in the course, we really take half the semester almost to just develop the precise theory of how points are arranged on a line. And so the stuff we're proving tends to be really not, none of what it is surprising or necessarily earth-shattering, which is part of why I was motivated in this paper to kind of talk about, what is notable here? What's going to be interesting to students to really engage them when, in fact, we're unpacking such basic ideas, and it can really feel like navel gazing at times. One of the axioms that I talk about in the paper basically just says if you have three collinear points that are close enough, one of them's between the other two, which if you kind of think about points on a line, again, that seems really obvious. But then the point is, by ratifying that as an axiom, that holds ramifications for kind of what must happen in the rest, in things that we will call a plane. And I want students to somehow be able to reflect on that relationship between assumption and kind of meaning in our planes.
Yeah, and you draw the connection in the article to school mathematics and high school geometry, and how sometimes students are turned off to proof pretty early on because the proof starts out by proving these really obvious things. The students are like, why did we have to do all that work to prove this thing when it's just obviously true? So it's kind of like trying to say that proof is for convincing, but they're only proving things that they were already convinced about, so it doesn't really do any convincing. And I think what you're doing here is you're showing, okay, we are proving these basic things, but the goal that we're working towards is not actually to just convince ourselves of these things. It's to build this whole theory. It's to actually explore the implications and the relationships between things. So when you move the target from just the truth of the theorem, you establish the target to be this theory building and really this meta-mathematical process, then you can really engage students in it. Am I kind of on the right track there?
Yeah, and I think, that's very much in line with my goal. And then methodologically what I have to do is try not to shove those questions down students' throats so much as to say, can I create a learning environment, can I create a set of tasks where, in fact, students really problematize those questions, where, in fact, those questions really flow out of what it is the student is trying to do. And that's a challenging goal, but I think it's really important, and I found it to be really fruitful. I want students to perceive the game of mathematics by doing it, by engaging in it, but then somehow giving them tools where they can really wrestle with these questions that to me are essentially mathematical. They're very much a part of what it means to do mathematics, and yet they're kind of maybe a strange way of approaching the question, if that makes sense, because to go back and kind of want to structure not only our, what we believe, but exactly how all our beliefs are related to all our other beliefs, or how our observations are related to other observations. It's a really powerful tool, but I think it does take work to really help students engage in that game in an authentic way.
Right. So, and to go through that work, you were doing this teaching experiment. Have you been doing this for years, and you've been going through multiple iterations, or can you say just a little bit about that teaching experiment? Yeah,
so I've alternated basically between large group and small group semesters. I'll do a semester where I teach the course, and I, try to pilot kind of my activities, but I'm not able to gather as intensive data about student learning. I can kind of get assessments and talk with students. But then in between, what I'll do is I'll run teaching experiments in kind of a more traditional sense, where I'll take 2 to 4 students out of someone else's course, and I'll just kind of teach them ahead of the regular lectures so that I'm still kind of getting their learning process as it's happening. And so then that's a nice experimental place to kind of try out activities, really see how students make sense of things, and videotapes. All the data in the paper comes from one of those small group semesters where I had a group of students that we just met over a couple of weeks and went over some of the learning activities I've been piloting. and just saw some really, really neat stuff emerging in their thinking.
My guest is Paul Dawkins from Northern Illinois University. So now that sets us up well to actually talk about some of the things that you saw when you were working with these students. So I'll start off with episode 1 from your article, and this is the students grappling with the idea of betweenness and going kind of back and forth, really trying to understand that idea. So what did you see, and what were the larger points that you took from this episode of betweenness?
Yeah, so again, I mean, they're defining what seem to be pretty basic ideas, what it means for one point to be between two others. And one of the challenges of proving in geometry is that students' kind of spatial intuitions are really prominent in their thinking. Like, they can just see in a diagram when a point's between, but to actually define that, not only is it hard to unpack what that means, it almost kind of seems odd to do it. And so originally then, what came up is we were really trying to define two different kind of coupled concepts, segment and between. Because students said, well, the segment is the two endpoints and all the points between them. And I said, well, what does it mean to be between 2 points? And they say, well, if it's on the segment, it's between. And so they kind of run into this circular defining. And, it leads students to kind of first recognize that their own ability to articulate what these things mean is limited. And one of the students in my study kind of had this moment where he was just saying, between, I think, means something different in math than it does in just everyday language, that he's starting to really reflect on the limitations of his own language. And so then there's this need to say, well, what else could we use to somehow define these things in a way that kind of gets out of this circularity? One of the students brought up a set notion, he really made a metaphor with intervals on like the number line. That maybe a segment could be kind of like the set of numbers that are between numerically. But the problem is points aren't really related by an order relation. The less than relation doesn't relate to points. So that led students to say, well, maybe if we look at distances, which are geometric kind of things that are numbers, then we could get order relations and let order relations somehow help us define between, which is a really fruitful idea. And it was cool how it made them kind of focus on what these things are, the difference between a point as a undefined object, a distance as a number, and a segment as a set. That kind of underlying mathematical structuring is, of course, super important, but a lot of times is a little bit invisible to students. I've found in my experience, at least, it really can be invisible to students. So this defining activity led them to really think about that, and they had an initial conjecture that, like in the Euclidean case, certainly worked. They said, well, if the distance from A to B is smaller than the distance from A to C, and the distance from B to C is smaller than the distance from A to C, then B is going to be between A and C. And one of the students kind of said, well, that includes points not on the line, so they added the caveat, B needs to be on the line connecting A and C. But in Euclidean cases, that actually uniquely characterizes points that are between A and C. So their definition descriptively was very good, but it's not the definition in the book. And this all actually came up because they were trying to, the other kind of question they had going was they had defined the triangle inequality when the sum of the two shorter distances, or sum of two distances is less than or equal to the third distance among 3 points. And I had posed the question, well, when are they equal? When is the sum of two of the distances between 3 points equal to the third distance? And they had said, well, that only happens when you're on the segment and when you're between. And so for them, they had kind of proposed a theorem that AB plus BC is AC. In other words, the distances add up to equality only when the middle point's on the segment or when it's in between. And then they wanted to define between otherwise, so they came up with these inequalities. So now they essentially had treated the book's definition as a theorem. They had they'd come up with this new definition that in some sense was good, but in fact, I kind of knew from my own experience that definition was not sufficient to prove the claim that they had made that between entailed equality. So it's kind of this cool opportunity where, giving them the reins and really putting them in charge of what they're doing, they rediscovered key ideas, but they also kind of understood them in this very different relation to each other. And so the game of defining really opened up the opportunity for them to reflect on how these things relate to each other. And in the end, basically what they do is they prove that the definition they came up with is not enough to prove the standard definition, the definition in the book. They didn't know it was in the book, but that's how I was thinking of it. But that the definition in the book can prove their new definition. And so then they set up, provability relation. One thing is provable from the other and not vice versa, which is what in common math parlance we call a stronger definition. And so they said, well, if that's the relationship between the two definitions, we should choose the stronger one. And so without me saying, hey, this is the definition of the book, they really said this definition has properties that the other one doesn't have in this kind of entailment sense that one entails the other. They didn't, again, use that word, but the point is it was cool to see how the mathematical activity really did lead them to engaging with these very familiar ideas of how we talk about mathematical concepts kind of in the abstract.
I'm also curious, and this comes up in the paper, but how would you say that your students talked about, or how did they think about axioms and theorems? Because I know that's one of the larger goals that we talked about at the beginning, about kind of making axioms a part of this whole mix and not just putting all the attention on theorems. So how did they talk about those two mathematical entities?
Yeah, and what I'll say about it is, that shifted over time. That as they engaged in the activity, it changed the way they understood those things. Because I think a mistake it's easy to sometimes make in something like math ed research on proving is to say, what are students' conceptions of axioms? And the real answer is when they come into my class, they don't really have a concept of axioms. In the teaching experiment, they kind of come up as rules. I just say, okay, what are basically rules that we should make about any distance function, or what are rules that we should make about how points and lines work? And really they're simply trying to describe phenomena that they see in the familiar plane. So you have prototypes that you work from, Euclidean, spherical, hyperbolic, and you say, how do things work in all of these cases that you would say, really, that ought to always be the case. Or axioms sometimes are just, a statement that's kind of intuitively obvious. One of my students basically said the triangle inequality, what had happened actually is they were presented with a plane in which the triangle inequality is false, and that really for at least one of these students was really a touchstone of why this plane was so strange, why it was so counterintuitive. And so he kind of then said, well, then we should always assume that the triangle inequality should be true, because that then kind of discounts this plane that says this plane is really not a good geometry because it has these weird properties. And so axioms emerge for them as the difference between kind of good planes, the prototype planes, versus these kind of strange things that we bring up during the class.
It's like acceptable behavior versus unacceptable behavior.
Articulations of acceptable behavior. So you can think of them either as just rules that they want to impose, or it's just articulations of geometric intuition that, sure, this seems like it should always be the case, just intuitively or spatially. And so,
but they exerted some control. Like they actually had input onto what those would be, though, rather than those just being handed down to them, right?
Yeah, no, I found ways to kind of make sure that they had ideas. We did kind of guided reflection on the familiar planes, but then I set them up to say, okay, you get to articulate what are our rules. And for the most part, students, they state a lot of the basic axioms that are in the text. And I have specific activities that if certain ones don't come up, then I kind of prompt them to talk about it. For instance, symmetry, they tend to not notice that, when they're thinking spatially, there's no reason to state that the distance from A to B needs to be the distance from B to A, because that's just obvious, because spatially, distance is the space between. But technically, formally, if you aren't assuming what distance means, you need to state that. So I have ways to kind of get them to unpack and just give them. I actually do this activity on a subway system, calling a subway system a geometry, and say, well, should it take the same amount of time for the train to get from station alpha to station beta as it does to get from station beta to station alpha, or something like that. I find kind of a somewhat situated context for them to think about it.
I think it's great that the students can actually feel some connection to the axioms rather than just having them handed down. And even here, when you kind of your guiding and you have things in mind that you're setting up, but even as you're doing that, you're giving the students an actual intellectual reason that the students can grasp for why this axiom is important or why this axiom isn't important or whatever. I think it's back to that necessity principle that you cite in the paper.
Yeah, very much so. And in the semesters when I do this with a small group, and they're actually in a different class, they get really excited when they go to class and the professor starts lecturing on the first axioms, and he presents them in kind of the classical way of doing this kind of course, and the students think, wow, we basically came up with everything he just told me. And the students certainly feel a sense of pride and accomplishment in that.
Mm-hmm. And I think I cut you off earlier. You were going to say something about the theorems as well on kind of the other side of it.
Yeah, so theorems, essentially, I mean, if you kind of ask yourself even formally, what's the difference between an axiom and a theorem? If you kind of take the formalist approach, an axiom is something to which we just assign a truth value. And then if proofs are truth-preserving arguments from assumptions to conclusions, then theorems are simply statements that receive their truth value from axioms or from other theorems. And so in the reinvention setting, it's just really the difference between, are we just going to all agree that this is an axiom, or are we going to try to prove it? And to some extent, that was up to me whether I said I'd task the students with try to come up with a proof of this. And there were two real learning opportunities that came up during the teaching experiment that led to the fruitful kind of reflection I really wanted. One was when students proposed a theorem as an axiom. In other words, what in the book is a theorem, so it is provable. They said, oh, we think this is intuitively obvious, so it should be an axiom. And that provided me the opportunity that I kind of describe in episode 2 in the paper of saying, okay, I want you to write a proof of this axiom, which they did. And then when they did, saying, well, what does that mean if we can prove an axiom? And so again, they're reflecting on their own mathematical activity, but I'm wanting them to sense make about what these labels really mean. And the other key opportunity that then is in episode 3 is when students feel like an axiom ought to be provable. In other words, for years, centuries or millennia, people thought that Euclid's fifth postulate ought to be provable. It just felt like it was not like the other axioms. It just felt like it ought to be a theorem. And so people tried a long time to prove it. And hyperbolic geometry actually grew out of people finally saying, what if we assume it false and treat that as not as an absurdity, but in fact a viable mathematical alternative? But in my studies, students will look at certain axioms and say that seems intuitive. It feels like we ought to be able to prove that. Not a lot, but when it comes up, that's an opportunity to say, well, how could we know if a statement is provable or not? Obviously, if we find a proof, we prove it's provable. But if, in the case of calling something an axiom, saying that we aren't going to prove it, it would seem like we'd want to say that it's not a theorem in disguise. It's not something we could have proven if we were just more clever. And so that, again, provided this interesting opportunity to kind of have students reflect on, given just a claim, right? If I just have a conjecture or a statement that I think is true, how do I know which category it goes in? Which bin do I put it in, axiom or theorem? And students start kind of using intuition to guide that, but later on we develop more sophisticated tools for how to do it.
That would just be really fascinating to see with students for them to actually go to that next level of not just, finding a proof or not finding a proof, but actually talking about provability and non-provability. That, to me, is just really fascinating. Part of why I enjoyed really reading your article.
Yeah, and it's exciting when it happens because, like I kind of mentioned, I've been interested all along in pushing the boundaries of what's possible in terms of students' mathematical learning. And when it kind of came up through the instructional settings, opportunities to really devolve to the students the task of thinking about kind of these theoretical relations among mathematical statements, it was really exciting to see that there really are kind of great opportunities here. But I will also say, having done this a lot, it's not real easy to just manufacture always. You really do want it to come out of what the students are doing. And like the realistic method kind of principles would kind of put forth, I really want it always to be rooted in students' mathematical activity and not imposed so much from the top down. And so there's real challenges there. I don't want to underplay that, but I do want this paper to be kind of a existence proof, if you will.
Mm-hmm. So you have this existence proof here in the For the Learning of Mathematics article. Do you have some other resources that you could direct us to that have come from the same line of work?
Yeah, so another piece of this, this paper really focused on some of the kind of particular mechanisms kind of at the local level that guided students' discovery about particular topics in the course. But I also have been working on trying to really look at students' view of the game of axioms in some sense more globally, kind of how they interpret the overall game, because and so there's a chapter that's going to be coming out in a MAA notes volume edited by Bonnie Gold and a couple of others, where I kind of from a practitioner standpoint talk about some of the important things I do in this course, but also I provide kind of a categorization of the ways students thought about the axiomatizing activity. Specifically, some students really kind of unproblematically said, the reason we're doing this is because it's a math class, and I'm supposed to do these activities because they're math tasks, and so they kind of have this mathematical frame. But other students then really thought of axiomatizing as kind of this formal game of modeling or describing the familiar planes. They really saw it as, we're just building this abstract hypothetical deductive, they wouldn't use those words, but, hypothetical deductive description of what makes Euclidean spherical and hyperbolic space work the way they do. That this is still kind of referential or descriptive in kind of the realistic math ed language. They talk about referential thinking. But then later on, as we really reflected on our activity, that students began to then really think about this, maybe more the kind of epistemic view of what axiomatizing does for us, is this idea of really isolating what are the intuitions or what are the basic theoretical building blocks of a theory of geometry. And this idea that, in fact, axioms can kind of stand in for spatial reasoning in this kind of powerful way. And so, their thinking doesn't get quite that formalized because we're not doing meta theory in the class. But I want, the students to see kind of the forest for the trees. And I want them to get some global picture of the game being played as we play it. And so, at least in that MAA notes volume, I kind of talk about some categories of the ways that students kind of reflected on the game, and maybe at a more global level, kind of thinking about what it is that we're doing in an axiomatic class. Because I do find, one of my other kind of motivations here is I think even students who are successful in some of our proof-based courses, I'm not sure that they always could really articulate for themselves what is kind of the purpose and what are the rules of proving. And I'd like to give more of our students, especially those who are going to become teachers or those who are going to go on to be graduate students, more of that kind of high-level awareness, at least for themselves, to sense make about the nature of the game and the rules of the game as they're playing it.
Mm-hmm. The scholar is Paul Dawkins. The institution is Northern Illinois University. The journal is For the Learning of Mathematics, and the article is When Proofs Reflect More on Assumptions Than Conclusions. Paul, thanks so much for talking about your work. I do have one last question for you.
Okay.
And this is a question that comes from my friend Aaron Brackenecki, but I have stolen it from him and I use it all the time. If you were not in mathematics education as your career, what would you see yourself doing instead?
That is a very difficult question because I think of myself as a teacher pretty wholeheartedly. So it's hard for me to imagine not teaching. I could see myself teaching maybe other subjects. I don't know, maybe philosophy or physics, but that's not very far away. I could see myself teaching in grade school. I don't know. I do teaching also related to my faith on the side. So I don't know. It's hard for me to imagine not teaching. One of my main hobbies that I probably could invest more time in if I really let myself would be board gaming, because I think of strategy board games almost as kind of axiomatic systems, so it kind of feeds the mathematician in me a little bit.
Oh, yeah.
Maybe I'd be into designing board games. I don't know. If you can just say whatever you want, then you can be as unrealistic as possible, right?
No, go for it. No, there's actually, in my office is Chris Bowling, who has actually designed a game, and he's getting it printed up very soon, so I've asked him for, a reserved copy. But hey, you can dream big.
That's right.
Then you could just hold classes where you teach everybody to play your board game.
So there is a lot of informal learning that goes on in such environments, that's for sure.
Yeah, well, at the next conference, if people catch Paul Dawkins, you can corral him and have like a board game night or something at the conference. I think that'd be fun.
I have not indulged myself in trying to mix work and play in quite that way. So.
Right, yeah. Well, Paul, thanks so much for taking the time to be here and speak with us.
Yeah, thanks so much, Sam. I appreciate the opportunity to share.
Thank you for listening to this episode of the MathEd Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.